Good evening, everyone. So, I'm pleased to announce our speaker of today. It's our very own Gaurav Bhatnagar from Ashoka University. He will be talking on elliptic enumeration and identities. Over to you, Gaurav.
Okay, let me see if I can. So can you see my screen?
Yes.
Okay, so thank you very much. Um, so I'm trying to experiment by, maybe I may need to write something. So this is joint work with Archana Kumari and Michael Schlosser. And um, uh, the, well, it's the same thing twice. So there are three parts to the talk. The first part is elliptic enumeration. And uh, the point I want to make in this talk is that whatever we do in elliptic enumeration and series is not very far from uh, it's not very far from what we do in Q series, normal Q series, or in enumeration. So this is the point. So it's partly expository. I'm trying to explain stuff that we did in the context of how you might want to do it also if you are interested in elliptic, uh, moving to elliptic. So the first part is on Fibonacci identities. Again, as I mentioned, joint with Archana and Michael. And the simplest example of enumeration is what is the Fibonacci numbers. And the way it works is that you tile a 1 by n board and with dominoes or squares. So dominoes cover two squares and tiles one square. And Fn plus 1 is the number of tilings of an 1 cross n board. So here's an example. So 1 by 4 board, it can be tiled like this. So one, it has no domino at all. Then this is a domino. This is a domino. This is a domino. So domino covers two squares, and here are two dominoes here. And the total number is F5, uh, the Fibonacci number. And we can check that this actually is the Fibonacci number. So if you think about it, here's a n board. The last tile, so you can put all the tilings into two buckets. The last tile is either a domino or a square. And if it's a domino, then this the number of tilings with the number of tilings in this case would be Fn minus 1, because if you delete this guy, then there are you get a board of size n minus 2. And if there's no domino, you can just cut this, and it's the so we're taking an n board. So if you cut this last guy, the tilings are the same as over here. So the number of tilings of an n board are is Fn minus 1 plus Fn, and then this means that the recurrence relation is satisfied, and you can check the. So the key issue is what happens when there's just one box and when there are two boxes, and this matches up with the initial conditions of Fn plus 1. So that's why you get Fn plus 1 rather than Fn, because the initial condition. So there's this book by Benjamin and Quinn, which says proofs that really count. And that has a large number of Fibonacci identities proved using tilings. So a lot of our work was pretty much basis of that. And then Tina Garrett did a Q analog of that in an unpublished work. So a lot of her work also we used. Uh, and then we extended it to arbitrary weight. So for Q Fibonacci numbers, what do we do? So Q Fibonacci numbers, you tile the 1 by n board, and wherever there is a domino, we put a weight Q raised per k. When the domino is at the square k and k plus 1. So in this example, the domino is in 3 and 4, so you put Q raised per 3. And then 6 and 7, so 1, 2, 3, 4, 5, 6 and 7, so Q raised per 6. So at the kth place, if the domino is at the kth place, we put a weight Q raised per k. and the weight of the tiling is the product of all the weights of the dominoes. So whatever the dominoes are there, you put the weights, and then the weight, the capital W is the weight of the tiling, and that is the sum of the the product of the small w's. And the Fibonacci number, the Q Fibonacci number, is defined as the sum of the weights of all the tilings of an N board. So this is the weighted tiling. And in this case, you get Q Fibonacci numbers. So Q Fibonacci numbers, if you recall, they came up in work of Schur, and there was they're related to the Schur's proof or Schur's discovery of the Rogers-Ramanujan identity. So here is the example again for F5. So tiling of a 4 board, this is the weight, q raised per 0 here, q raised per 1 here, q cubed here, and q1 into q raised per 3 here, and you get the sum of the weights, which is 1 plus q square. So this is the fifth Fibonacci number. And again, we verify the initial conditions like this to see which Fibonacci number. So this is the Schur's recurrence relation for the Fibonacci number, Q Fibonacci numbers. So we can do pretty much the same thing with arbitrary weights. So we'll talk about elliptic weights, but first we'll just do the same thing with any weights whatsoever. So we define a small w, this weight function, the small w, and we put a small w k at the kth place where there is a tiling. So same thing, instead of q raised to the power 3, we have small w raised per small w sub 3. I put an f to indicate there is a Fibonacci number here, and capital W is the weight product of the weight of the dominoes, and the fn plus 1. So the weight of a tiling is the product of the small w's, and fn plus 1 is the sum of all the weights. So again, I've mentioned Benjamin Quinn Garrett, and I should also mention Seidler. He also has something very similar to this, where he did many identities. And this is unpublished work, but it's available on arXiv. Okay, so if we go back to Schur's work, there is a concept of an M-shifted Fibonacci number. So this is, so I don't know if you've, so there is some work of, so there is a Garrett, Ismail, and Stanton. They have some identities for shifted Fibonacci numbers, where this power is not just q raised to the power n minus 1, but it could be n or n plus 1 and so on. And so does so they have an idea of an m shifted q Fibonacci numbers, and they have some identities according which come up from which very famous identities for m shifted Fibonacci Rogers-Ramanujan identities. So how does that get defined here? We say that the first m squares have no domino. If the first m squares have no domino, and there is a m plus n board, 1 into m plus n board, then we define the m shifted Fibonacci numbers like this. And there is the concept of a fault in a tiling, which means that there is no domino at that point k. So if there is, so again you get the small weights and the the product of the weights and so on.
But Gaurav, aren't the M shifted numbers just the original ones shifted?
No, they're a little bit different. So I mean, they basically, if you think of orthogonal polynomials, 3-term recurrence relations, they start at some later point. So there's something which is the initial values are different somehow. So it somehow there's some slight differences which occur in the actual examples if you write them down. So this weight stays the same somehow. But so do you remember the Garrett, Ismail, Stanton identities? There is a M which is very much there in the sum. So they had so maybe I should say so this is Fibonacci, and this is the other so this is Rogers Ramanujan. In one of them there is no M, there's no N, so this is missing, and the other one has N square plus N, and in the shifted one there is an M here actually. So it's very it's just there's some slight differences, but they're really different. Okay, so we pretty much could generalize in very general terms, Fibonacci identities and get it for arbitrary weights. And here's an example of a theorem which is there. So we're considering a 1 cross m plus n board. So first m have no domino, and you count in two different weights. M is the mth position either has a domino or not. That's where we cut it. So on the one hand we get f of m plus n plus 1, because if we just consider the whole board, and if mth place has a fault, that means there's no domino, so we can cut it here. Then it's a product here. So this part will be fm plus 1, and this part will be fn plus 1, but shifted m. So you get this term. And if it has a domino, then we get this term. So there's a weight which comes. So this is I mean, if you just put w equal to 1, you'll get the usual Fibonacci type identity. And if you put w equal to q raised per m, you get an identity for the q shifted identity. So the proofs are very much the same as done in classically. And here is an example of an identity which was the most complicated one that we found. So I'm not going to give the proof, but why I like this identity is that it's a generalization of Cassini's identity. So Cassini's identity is the one which you use to prove that the continued fraction converges. And then it was generalized by Catalan, and then further by these people. And then here is the full generalization. So the interesting thing here is that there is a term which survives somehow after some cancellation. So in this picture, k is the largest common fault of both of these. So we are calculating the pairs of these guys, and we flip it somehow. And when we flip it, and if there is no fault, sometimes you get a positive sign, and sometimes you get a negative sign with these weights. So this is the most complicated identity, and more or less not very complicated is my point. So lot of the point is that the lot of combinatorics which has been happening in Q combinatorics can be extended to elliptic combinatorics or to general weights, and this is the program which Michael Schlosser and a few others have been following. And the key item here is, so in general, you can do this in this case, the general weights, but then how do we define elliptic weights? So my point is to show you how one would like to do elliptic weights. So where are we? So in so this is the part where things are different from Q analogs. So we start with this modified theta function. I will explain where it comes from very quickly. Very shortly, and it satisfies this quasi-periodicity and a 3-term addition formula. This is due to Weierstrass. So this very symmetric kind of thing. There are two products here, a p raised per j, so 1 minus a p to the j, 1 minus p to the j plus 1 over j. And so where does this come from? So it shows up in Jacobi's triple product. So here's where it comes from. So if you take sine pi z over pi z, and you write it as an infinite product, so you'll write it as 1 over v square over n square. So n 1 to infinity. So you can think n going to z, but it doesn't converge. So this is the right. So this is 0. So sine pi z is 0 when z is equal to 0, 1, 2, 3, 4, -1, -2. So it's the simplest function, which is 0 with zeros at a arithmetic progression. And if you look at this function right here, it's the simplest function which has zeros at a geometric progression. So in that regard, it's a very it's a very natural function to consider, and it comes up. So there is a famous result called Jacobi's triple product where this result comes. So this, I mean, I'm using this Q rising factorial notation here for this product, infinite product. It converges for absolute value of Q less than 1, and in fact, this is an analytic function in Z, except when Z is 0. So you can write it as a Laurent series, and then it's fairly easy uh, to see the quasi-periodicity. So if you replace Z by ZQ, then in the product, most of the terms cancel and you get -1 over Z theta of Z sub ZQ. And then if we compare coefficients of the Laurent series, we can get a recurrence relation for n. So n bigger than 0 and very similar one for n. The same one, in fact, for n less than 0. So it boils down to calculating the constant term of this series. So, all other terms are in terms of the constant term. And to calculate the constant term, just think about it. If you look at, if you write down the product, the constant term will take one term from here and one term from here to cancel the z's, right? So it will be of this form. The constant term will be of this form: q raised per a1 plus 1 plus to ar plus 1 times q raised per b1 to br, where this part is coming from here and this part is coming from here, and a's are ordered somehow. And this is actually, if you're this you can do geometrically by considering a partition. So if you think about this, this represents this partition. So a1 equal to 5, 3, 2. So you take any partition and you write what is called the Frobenius symbol for the partition. So you take the diagonal entries and then you just write down the number of boxes on the right of the diagonal and below the diagonal. So these are the B's, below the diagonal are the B's, and above the diagonal are the A's, and they're exactly K entries here. And so this is really a partition. So the coefficient of Q raised per n in A0 is the number of ways of writing n in this form, where R is the number of boxes in the diagonal, and that's actually a partition of n. So A0 has to be 1 over QQ infinity. Once you put A0 equal to 1 over QQ infinity, you get a proof. The proof gets complete. So it's called triple product because there are 3 of them. And then this is a sum which is very useful in number theory. So this is due to Gauss, perhaps, and Jacobi, and it's a very central thing in number theory. And I mean, there are ways to look at the sum as a discrete analog of the normal distribution. So if you just think q replaced by q square, you get, and something you get q raised per n square, k square here, and z raised per k, and then it's a discrete analog of the normal distribution. So it's somehow very central to everything. So how elliptic Fibonacci weights come about? This is what the Fibonacci weights are, and I'll again explain why they, what brought this up. There are some consideration, but this is the weights which is an elliptic, which are the elliptic Fibonacci weights. So there are some ways, and they have two additional parameters, a and b. Addition to p, which is called the norm, as well as the Q here. And if you put P equal to 0, so in this theta product, if you put P equal to 0, you just get 1 minus A. So if you put P equal to 0, you get this product, this weight function. If you further put B equal to 0, you get this thing which we call the weight with A. And if you put A equal to 0 here, we get something like this, which is what, and if you put both A and B 0, then we recover the Q Fibonacci. So the elliptic generalization has these weights which are sort of products of theta functions, ratios of products of theta functions, uh, and uh, uh, and they have two additional parameters A and B. And where do these A and B come from? So there are two considerations. So one consideration which we had was that we need to uh, a lot of Fibonacci identities can be proved by telescoping. So I have a paper on telescoping on a very simple idea of Euler, which shows how to telescope any sum manually. I mean, not using the computer, but just manually. And here's an example of doing a Fibonacci identity there. And then we basically said that, okay, what should the elliptic extension of this be so that it fits this Euler's lemma? So this is in a paper called In Praise of an Elementary Identity of Euler, where I do a lot of, lot of telescoping sums going up to even using how to do WZ method by hand using telescoping. And this is what is called the telescoping lemma. So all telescoping sums follow this pattern. So all we have to do is find this pattern. And here's a proof where if UK is Fk plus 2 and Vk is Fk plus 1, then we get this identity. Sum of the Fibonacci numbers is Fn plus 2 minus 1. So all Fibonacci numbers, identities, more or less all can be proved using Binet's formula, but many of them can be proved by telescoping too. And in fact, any identity of a certain kind can be proved by telescoping. I'll show you what I mean by that. So one is this consideration. The other consideration is this theorem. This is a classical theorem that if G is an elliptic function, that is a doubly periodic meromorphic function, then G has to be of this form. And there is an elliptic balancing condition. So it's a elliptic function in a multiplicative sense. So if we write Q as e raised by 2 pi I sigma and P as 2 pi I tau, then G of X is doubly periodic in X with these periods, sigma inverse and tau over sigma. So these are theta functions, the modified theta functions which come from Jacobi, and there is a elliptic balancing condition which has to be there. So these two conditions require us to have an A and B. So the minimum thing which we need is something like this, and we need the A and B to be able to get something non-trivial which is elliptic. So this suggests what the weight should be. And in fact, Michael Schlosser and Misu, you had a elliptic Fibonacci definition, but we modified the definition mildly so that this proof fits. And when this happened, then we got a bunch of new identities, which many of them we could prove by telescoping, and most of them we could prove by other means. But we could discover a lot of identities very quickly without any trouble by extending the weight. So to summarize, the weights the small weights somehow have to be have these two additional parameters, the A and the B, in addition to the P and the Qs. And the requirement is, they all look very similar. The requirement comes a lot from this classic theorem. I think it's due to Weierstrass, maybe, I don't know. It's there in Whittaker and Watson. Okay, so I should say, so I'll go on from here. So this has already been published. It's come out in Journal of Difference Equations and its applications. and we give some more identities of the kind. So now let me go on to elementary identity. So the elliptic identities, that's the part 2, and the first one is again with Archana and Michael. So now we've got a lot of Fibonacci identities. We could get them through telescoping, and a lot of these elementary identities also can be done by telescoping. So these are examples of what are called which have no I mean, these are the simplest elementary identities we were looking at were things like sum of integers and things like that. So this is how we define an elliptic number using this uh, geometric sum, and then we have an elliptic number. So this is the Q number. The elliptic number is defined like this, again through similar things. And when I say the elliptic number, this is, I mean, you could have some modifications in weights, but the motivation of these weights is that x plus y is equal to x plus w times y. So W is this weight. And then this identity comes straight from Weierstrass three-term recurrence relation for theta function. So this is, I mean, we would like x plus y to be equal to x plus y. And the Q identity, the Q number satisfies x plus y is equal to x plus q raised per k, q raised per xy. So both of these, together define the elliptic number. So the elliptic extension of this identity is this guy right here. So this capital W should be viewed as q raised per whatever is in here. So q square, q raised per n minus 1. And this elliptic number n is a generalization of the q number or just the number. So, okay, so here's an identity. Simplest one possible is sum of odd numbers is n square. This is the generalization with the weight function which I described. And I just want to go over some of the special cases so that you know what all we have got over here. I mean, all this is, I mean, the proofs are trivial pretty much. They're straight from by telescoping. They are set up for telescoping, in fact. But what you can do is you can take p equal to 0, for example, and get what is called the ABQ analog. So you get something which looks like this. So these weights are I defined earlier. AQ analog is when you take b equal to 0, and BQ analog is when you take a equal to 0. And there's some confusion always in these notations because the AQ analog and BQ analog should be, they're different. So I put a bracket around the BQ analog. And let's take more special cases. Suppose you remove the A, then you get this guy. So this is the Q number. If A is 0 in the AQ analog, then you get something slightly different on this side. If A is 1, you get, well, you no longer get n square on this side. You get n plus 1 cubed and n plus 3. And similarly, if you take b equal to 1, you get something else. So these A's and B's are adding a lot of new identities to the whole story. And if A is Q, then you get something, product of 4 terms on top, and then this ratio of 2 terms here and 2 terms here. So it's yeah. So I mean, when we get elliptic identities by hook or by crook, the special cases are like just they have 2 additional parameters A and B in addition to the Q, and that means that it's generalizations of Q identities. So here's another one. This is this is classic telescoping kind of identity for rising factorials, and we get something very similar. And then rising factorials in the denominator, we get something very similar. So the proofs are quite easy. They follow from Euler's telescoping lemma. And these are quite easy in form. However, this one is quite modifying. So So this is the worst one we could get. I mean, the most complicated one we could get using telescoping. And if you see, this is not even hypergeometric, because if you look at it, it's got this quadratic powers inside this thing. So remember, this is in the A, B, everything 0, Q case, it's 1 minus Q raised power a quadratic power here. And then it's, you're multiplying it. So it's not a Q factorial form. So I mean, it looks like hell, but in some sense, it's easy. And in special cases, so this is the hypergeometric special case, it's an elementary identity. And it gives you a lot of these kind of identities, so this is like a sum of cubes identity. So, and I mean, it gives sum of cubes as well as sum of natural numbers. And so all these are contained in this. So here I've defined n plus 1 choose 2 sub q as n sub q n plus 1 q over 2. And this is slightly different. As you see, it's n into n plus 1 sub q. So as a q number. So the q identities are also very strange. And again, these you can get lots and lots of such identities over in this text with this just telescoping. So this was so we called this an esoteric identity with many parameters, and it's going to appear in New Zealand Journal of Math. Okay, so third part of my talk, and it's okay. So I'm making good time, I guess. So the third part of my talk is also on the same theme, but this time without Michael Schlosser. And this is the latest thing which I've just uploaded recently on archive. This is with Archana, and these are hypergeometric. So the third type of identities which we consider. So first we considered Fibonacci, then we did telescoping, which were the elementary identities, and now we're getting elliptic hypergeometric identities. So what are elliptic hypergeometric identities? Again, Q rising factorial same as before, theta modified theta function same as before, and we define theta rising factorials like this. So if P is 0, then this comes down to the Q rising factorial. So if P is 0, then it's 1 minus AQ to the J product. So it's 1 minus A, 1 minus AQ, 1 minus AQ square, and so on. And we define very well poised elliptic hypergeometric series. So instead of the phi, we use the V, and or rather, this is a W which is used in one variable for well poised, and we use a V, and it's got this as the special parameter, which is the very well poised, and there is a balancing condition. So you can see A1 and QA1 over A6. So A6 is linked with QA1 over A6, and AR plus 1 is linked with QA1 over AR plus 1. So this is the very well poised part, and there is a balancing condition. The product of all these things should be equal. So, and this compressed notation, I guess I already used before. So product of the theta function. So now you have QP rising factorials, and when P is 0, it is the product of, it's a rising factorial, the usual rising factorial. So each, right. So, so let me say that what we are, so we are looking at these series. So tk plus 1 over tk, this is a rational function of k. That's hypergeometric. If it's rational function of q raised per k, it's q hypergeometric or q series. And here it's looked at as a rational function of elliptic function. So this is it's a rational function of elliptic functions. So if this is elliptic in k, so now k being regarded as a complex variable, then it turns out that these are naturally defined. I mean, this is the way it has to be because of that classic theorem which I mentioned that they have to, elliptic function has to be a rational function of theta function. So these are called elliptic hypergeometric series, and if you put p equal to 0, you get q hypergeometric, and then further when q is 1 with some changes in parameters, you get hypergeometric series. So they're at the top of the hierarchy as such. And here are the more, I mean, if you're used to playing around with basic hypergeometric series, then these are the identities which you use essentially. And these identities work out in the elliptic case also. So the point I'm making is that conceptually it's no different. I mean, in practically it's no different to work with elliptic hypergeometric series as with Q hypergeometric series. The same identities pretty much with an additional P work. So all you need to do is to, even though these are like infinite products and so on. So the motivation for this work comes from some work of many authors actually. The main where we noticed it was that many people were such as Wang and Yi. So this is Likuan Wang and Eja Yi. They found some Hecke type identities. So this is a Hecke series, and this looks like a half a. I mean, this looks like a theta function, and there's some more theta type of functions. And so these kind of functions, identities they found using work of Liu. And Liu had this series. So these are examples of Liu's work. So there is a 3phi2 on the left hand side with some infinite products, and there's a sum of 3phi2s. And similarly here, there is a 3phi2 as a sum of some hypergeometric terms, some very well poised terms. So these were not in Gasper-Riemann. So these identities are not in Gasper-Riemann. And Liu found them, and Liu found them in a very strange way. He found them using his own technique of how he's developing Q series. So it's not only Liu and not only Wang and Yi, but Liu found special cases of his work were which were very different from. I mean, he found some generating functions for Askew-Wilson polynomials. He showed they're important. His work. So our work started when we saw that Liu used some Q derivative operator methods, and there are actually just two very useful identities of Liu, and special cases have been shown to be useful by many other people. This is not liquid. This is Likuan Wang. Now what Jin Wang, another Wang, and Ma, Xinron Ma, what they did, they had a very strange approach uh, to get identities, and they sent up. They have a long paper on archive, which I think is still not published. It's been around. I mean, that paper, and they use some Q Lagrange type techniques to get one of Liu's general expansion formula. So that is what interested me. That my interest was that can we generalize to multivariables. So whatever Liu is using these Q derivative operators, I don't know how to generalize to multivariables. But if you have Gasper-Riemann type of techniques, then I can generalize to multivariables. So what Jin Wang and Ma have done is they use some Q Lagrange type identities, and then Gessel and Stanton's work on Q Lagrange inversion was much clearer. So their work was not so clear. I mean, what they were doing, it was a little confusing. But in joint work with one of my students, Surbi Rai, we cleaned up Wang and Ma's work, and we found that you could convert it into something which used matrices, and the matrices used were an equivalent form of Bailey transform. And we also used the balanced 3p2 summation theorem. So So we were able to we used Jin Wang's approach and we codified it and we got one of Liu's results, and then we found that a slight modification leads to the second formula of Liu also. So both the useful identities of Liu we could do by this technique. And then we I mean, in one variable we did it, and then that basically the paper was essentially the context of root system, so with several extensions of Wang, Ma, and Liu. So all these things, these bits and pieces were available for root system. So the Bailey transform matrices were defined by Steve Milne. Balanced 3p2 summation theorems of various kinds were available, some by Steve Milne and others. There were a couple of more. So the technique, let me say, is I mean, we codified in the form of a lemma. So we have a pair of infinite inverse lower triangular matrices. So this is the pair F and G. And small fk is some analytic function, which if you replace y by q raised per n, you get the same matrix, F and k. And k, h, and beta are some more general things. The only thing required is that h should be 0 when y is q raised per n, and for j bigger than n. And they either the series terminate or they are analytic functions of y. And what we did was that we choose h and so this G and this F is pretty much determined by this Bailey matrix. The K and the H and the beta can be chosen, and beta can be left general. And H and K pretty much need to be chosen so that the inner sum gets summed by the 3p2. So that's what gives you gave us the Wang and Ma result. So slightly different language we wrote it, but it was essentially this idea was there. So I mean, this complicated thing, you know, it came from a complicated way of thinking, which Wang and Ma did, and we just cleaned it up. So now what we did was we wanted to do in this paper, we wanted an elliptic extension of what Surbhi and I did in one variable first, and then we'll look at multivariables later. So this is our result. There's a general sequence AJ, and there is this sum on one side and a double sum on the other side. And there are these theta things which correspond to, these correspond to the a very well poised part almost. And when the, AJ is a delta function, which means it's 0 unless j is equal to 0, then this boils down to a 8phi7 or elliptic 8phi7, which is Frenkel and Turev's 10v9 summation theorem. So it's an extension, and you can, if p is 0 and b goes to 0, it reduces to the formula, some of the formulas of Liu. And how it's different from the Q case. So in the inner sums, we use an elliptic. Before I say how we get it, you say if AJ is chosen such that this inner sum, this one is summable by a 10v9, it gives a transformation formula also due to Frenkel and Turev. So it's very, very linked with the two fundamental theorems of Frenkel and Turev, a 10v9 summation and a 12v11 transformation. So they correspond to, in the Q case, they correspond to 8phi7 summation, which is called Q analog of, it's a Dougal's result, and a 10phi9 transformation, which is due to Bailey. So the proof, so here's the thing. So the Bailey lemma, the Bailey matrices are not available in the elliptic case because they're too small, but there is an extension of Bressoud's matrix, which is the which is there in the well-poised Bailey lemma. So that has been given by Werner, and we use that. And instead of using a 3phi2, which is not available, we use the elliptic 8phi7. So these are like slightly technical things, but I think these are sort of obvious things to people who are working in the area. That elliptic case, we have bigger sums where it's well poised as well as balanced things have to be there. And the smallest well-poised and balanced thing is a 8v7 level thing, which is Frenkel and Touret's 10v9 summation. So we use that, and again the well-poised Bailey lemma is available in the elliptic case, but not the other Bailey lemma because that's too small. So if you so this was kind of obvious thing to try, and we used Bressoud's matrix inversion. So it's not very well known. So that Bressoud's matrix inversion is very related to the well-poised Bailey lemma. Somehow that seems to be missing. I mean, he's not got the credit so much as he should have. And but people in the know about this. So Werner had generalized this because it's such a central result. So the same thing can be rewritten to get a generalization of Wang-Ma's expansion formula. So again, double sum and we get a Wang-Ma. So if P is 0 and B goes to 0, it reduces to a formula of Liu. If P is 0 and C goes to 0, it gives Wang and Ma's expansion formula. And if B is 0, it reduces to another useful formula for Liu. So Liu had two useful formulas, and both of them get combined in one formula at the elliptic level. So, but we have to take P equal to 0. So it's more general than what Liu had and Wang and Ma had by using these new matrices. So yeah, so this is the main result which we have. Let me show you some obvious consequences. So one thing we could do is that we could take AJ to be such that this side becomes summable. So a lot of terms over here are, I mean, the terms are all elliptic and balanced, etc. So there's no problem. So we did that, and we got 4 such formulas. So there are 2 examples. So Ole Werner had a paper in 2005 where he had 4 such formulas, 4 summation formulas, which were all basic. So basic because they have base q square and q mixed together. And also norm was sometimes p square, sometimes p. So he had 4 such formulas, and all those 4 we could apply and in this inner sum and get 4 new formulas. So if we use the 10v9, we get back the Frenkel and Touret's transformation. So these are similar in that respect, and it was immediate to get these formulas. So we get 4 of these, and then we could also so we could get this so that the inner sum gets summable, or we could get this so that the inner sum is summable. So with the same formulas and maybe one more, we got double. So here we got a double summation formula. And again, Liu has some double summation formulas from his result, which he used for giving generating functions for the Askew-Wilson polynomial, new generating functions for Askew-Wilson polynomial. So we got inspiration from Liu's paper again. And again, we use, so here we have 5 of them, again using Werner's summations as well as the Frenkel and Touret summation. So let me say that getting so many makes us very happy, because I mean, Werner has 4 summation theorems, and so summation theorems are tough to get. I mean, everybody has like 1 or 2, and there's no general technique where you get large number of summation formulas. You get multivariable summation formulas which are infinite in number, but still, so they are much lesser than the, say, millions of formulas in Q and hypergeometric. So the elliptic formulas are not, few and far between, seems. So I think there is one general technique of some formulas where both sides don't look so different from each other. That is due to Chu and somebody else. But otherwise, the general techniques all involve the well-poised, matrix inversion and so on. And this is a general technique which gave us so many formulas very quickly without any trouble at all. So yeah, this is the reference which has just gone up on archive. And I think I'm ending well in time. So let me end by saying that the elliptic virus is showing many early symptoms of the Q disease. This is, of course, a joke on Ole Warnar. Okay, thank you.
Thank you, Gaurav, for a very nice talk. Are there any questions? So I had a couple of questions.
Yeah.
You must be knowing that Ankush Goswami, he obtained the Q analogs of this Euler's formula, Q analog of Euler's formula for zeta 2n.
Yeah, I remember that.
Is there an elliptic analog of it?
I don't think so, not so far. So, yeah. I mean, there are very few elliptic formulas, and all of them are balanced as well as this. So you need several parameters. So it may well be that a general formula which gives his things maybe has an elliptic thing, but I don't remember exactly how he got them. So yeah.
I think he first went with zeta 6 or zeta 2, then zeta 6, and then with zeta 2n in general.
Yeah, I mean, are they general? Are they special cases of some general hypergeometric formula? Then one would think, is there an elliptic analog or not?
Oh, okay.
So this is one thing that, you know, the old story of Knuth having huge number of binomial coefficient identities, and there were millions of them, infinite.
Oh, Gould.
No, Knuth also went. Yeah, Gold had, but Knuth in his book he went on and on about how to prove uh, binomial coefficient identity. It was quite a scandal, and then ASCII and essentially Ranjan Roy wrote an article saying that all of these are special cases of, you know, hypergeometric function identity. And so the philosophy which I find almost always works is that almost all these identities are special cases of some general identities. We may not know how they may have been derived some other way.
Yeah.
And
in fact, I mean, I was thinking about that other way around. So in case we have an elliptic generalization of elliptic analog of zeta 2n, maybe the very basic case, I mean, when we reduce to Q analog and to the hypergeometric case, perhaps it gives some new identities for the Riemann zeta function.
Yeah. I mean, definitely worth looking at to figure out. But yeah, Q analogs of Riemann zeta are not very pretty so far. Yeah.
And another question is, you showed the proof of Jacobi triple product identity using this. So who is this proof due to? Okay,
so yeah, so I'm not sure. It's been around. So I think maybe Andrews in his 10 lectures book, that white book, indicated this proof.
Okay.
But maybe somebody in the audience can answer that. I know it's not the proof in Andrews, ASCII, and Roy. There they calculate the coefficient. I mean, the key issue is calculating the coefficient.
Okay.
The constant term. So that thing is done by so somebody else may want to answer that. I mean, I don't know if Michael is there or Harmer.
So you said in Andrews?
No, I don't know. But I think I mean, since it's the round series, probably to do it formula, you have to be a bit careful with the convergence because you have different expansions, different underlie. So it's like a formal proof, but to make it rigorous, I think you need to do like one more step.
Okay.
That's
Okay.
So, but I would say the combinatorial idea must be in Andrews.
Oh, Michael is saying he cannot unmute himself. So, maybe do it through here.
There's no. Must be something wrong. Because here it's saying ask to unmute.
Yeah. Oh, Arvind is also saying they don't have permission.
How is that possible? So allow participants. It says allow participants to unmute themselves. Try again.
He's not able to.
Huh. So what do I do? I mean, I'm seeing a place where, oh, I can at least make you a, maybe I can make you a co-host.
Yeah, and then, but how am I able to unmute myself then?
Yeah, I have no idea.
And even Hjalmar was able to talk. So he's saying he's got the request, but he cannot unmute.
So now I've made you a co-host. So
Okay, maybe I can try then.
no, I've made Arvind and Michael the co-host.
Oh, okay. Oh, still not possible.
There's something wrong with your Zoom, maybe.
Yeah. Maybe they can write the questions here. If
Yeah, or comments. Yeah, is it a? It could be a Zoom problem.
Oh, he's unable to start the video also.
Okay, then it's the problem with it.
So let me see. Oh,
I
that's
should.
strange.
I mean, I'm okay. Let me stop sharing so that we can. I mean, I can.
Oh, okay. I figured out the issue.
Well,
What was it?
So there is that notice that comes. I think this is the same for you, Michael. There's this notice that comes saying this meeting is live streamed.
oh, you have to press
got it.
OK.
If you don't click on got it,
It
then
was on the side, so I didn't see it and I ignored it. But
Okay.
only when you click OK.
Then it
you are-
allows.
So Michael, if you click OK, then it'll work for you.
Oh, yes. Now, can you?
Yeah.
No. Yes. Thank you very much.
Yeah.
I'm back, or
So-
I'm in at least.
So,
Okay, thank you.
Which? So you have a question? Which?
Yeah, I have a question, but you had a question too, which I did not completely understand. Maybe I'm not sure because I came at 12 o'clock.
Okay.
But
So the
anyway, so
question-
this, yes.
Yeah.
So did you say how you're proving this identity,
Yeah.
this with the AJ?
Yeah.
Did you use the 8v7 or the 10v9 actually?
Yeah.
So it requires the 10v9.
It requires a 10v9.
Okay, so that means there's no by basic. I mean, there's a by basic version of Bersoud's matrix inversion.
Right. Yeah. So we
And
haven't tried that yet. Yeah.
Okay, and that might
That might work. Yeah.
work with similar
Yeah.
versions.
So I mean
like,
that you're talking about the summation theorem to use would be that telescoping sum.
I mean, yeah, like a version of this where you have an additional base,
Right.
which
Right.
you could maybe specialize quadratic. Okay, you had quadratic, but also cubic.
Yeah. So that we
Okay.
haven't done yet. Yeah.
Mhm.
So we wanted to get this first, and we'll look at that maybe. So in fact, the two key ingredients are a matrix inversion, which exists for arbitrary sequence, as you know.
Mhm.
And so you have not only bibasic, you have arbitrary sequences as parameters, which generalize Bersouds. And so A, B, A, K, B, K, C, K, etc. And then the inner sum has to somehow sum. And that also is available in arbitrary sequences, the
Okay.
telescoping sum.
And this AJ can depend on n, I guess.
AJ, no, it doesn't depend on n.
it must not depend on n. So
Yeah,
because the
it's
last
only-
sum, you
yeah.
could
Yeah.
cancel the n products.
No, you can't.
No,
So this
I'm
is
not allowed to do that.
yeah. This is so this indicates pretty much what you can allow. So beta AJ comes from the beta j, and that's dependent only on j. Everything else
But
is inside here.
it could depend on n or not.
No. So
No.
y is q raised per n basically in
Mhm.
this. So there's no y here, and here whatever y was there,
I
it has
see.
been replaced by q raised per something.
Okay, so you cannot cancel the two
Yeah,
numerator
these
factors. Yes,
right. So these
these
two are
last
the
two.
key issues.
Yeah, you have to keep
Well, no,
all of
these
them.
are okay. You can cancel the ends here.
Ah,
But
so that's what I
these
meant.
these are ones. Yeah. So yeah, this is cancelable. Yeah, absolutely.
So it can depend on n, but not
Yeah,
on,
yeah,
of course, not
yeah.
on k.
No,
But
I mean AJ cannot depend, but you replace B by BQN.
okay, so you can anyway get rid of that.
Yeah,
there.
you look at
Yes.
B over here. So there's a Q
Mhm.
raised to minus n, and if you replace B by BQN, you'll get a pair here and a pair here.
Yes, I see.
All the rest will go away. So this is like, I mean, badly written in some sense. Ideally, it should be BQN over here. But somehow I
Okay. And the last double sum, can you show that one more time?
yeah.
Yes. Yes, did you, could it, yes, like for instance, that or the other one. Are you sure that that's not contained, let's say, in one of the Gustafsson-Milne type of results that you have not checked?
Multivariable.
Yes,
No, they don't look like
like
multivariable.
the n equals 2 case.
Yeah. Well, this is like over a triangle, right? I mean, inside here. So these are
Yes,
not
well,
independent.
that's true, but there was another one which looked, yes, I think that one, like the B factors you could combine and the C factors on the right-hand side. And
I mean, that you combine to get some bibasic type of things or 2J or things
they
like that.
seem to give like an extra very well poised factor.
No, the very well poised factor is BC and A.
Yes, but you have another one with the B factors, isn't it? B minus B,
No.
BP minus B
No,
over
no.
P.
I mean, it's BC.
Ah, okay, I see. You don't have it.
Yeah.
So it's a base Q 2J. So it's sub Q 2J. Yes, I see now.
Yeah. But sub 2J, I mean, we didn't. So Ole, so these were all coming from Ole's work. And Ole, the way he wrote them was to make sure that the hypergeometric and the balanced nature shows up.
Okay, I see.
So he didn't combine them. Like we would do this in Q series, but we decided to follow his approach.
Okay, I see. Well, looks impressive, yeah. And so what was your question?
Yeah, the
before?
question was, so Atul's one question was that the proof of Jacobi triple product identity where the constant term is the generating function of partitions. Who is that due to? What?
Yes, so that might be Bruce Byrne. I think Yarma also mentioned it in his lecture notes or somewhere,
Halmer
or in
says,
a talk
no,
maybe, or in a tutorial.
No. Halmer
I
says
don't
this is
think
not
so.
there.
I don't
No,
think I
Yes.
mentioned
Halmer
this,
thinks
but
it's
I
not
know I've
correct, yeah.
seen it before.
Yeah, this proof that the constant term. So yeah, I remember I attended Halmer's. I was his student.
Okay. I have a book by
This is Andrew's probably.
yeah, Invitation to Q series by Hai Chi Chan. Maybe it's mentioned there.
Yeah, I think this is Andrew's because this is Frobenius partition, so he showed it at some point, and
in his
maybe ASCII doesn't think it's fully rigorous like Halmer, so that's why he didn't include it in the book.
Yes. So yeah, I'm not sure. Yeah, okay, I don't know now.
Okay. I'm pretty sure that this is, at least I have seen it in Andrews, whether he proved it on, I mean, whether he's given it, I mean, it may be some due to somebody else.
And one other question that I had was, does your general lemma with Surabhi or Archana, does that lead to more identities of the type of Liu and Yi?
Yeah, so we haven't, so in the current paper which I'm working on, we are looking at so these guys, Wang and Yu and other people, so all these identities are possible in Q series, right? And we have got multivariable versions in that. Now, these are very special cases you take and then you do some manipulations. So those special cases we are trying. I'm trying in using Surbi's results to see if we can get something close to this.
That will be very interesting because they have a structure of the Heka type.
Yeah, these are Hecke type identities.
Yeah.
And they're false theta functions, and these are almost like, I think this may be a mock theta function. And so in this paper, this is Li Kuan, Wang and Yi. They mention previous work along with you two, where you've got some partition functions from these kind of identities. So I'm saying that there's a clutch of papers which involve these identities, and all of them seem to be coming from Liu's work.
Okay.
And that is the reason why we thought, okay, let's just, so, I mean, one can get identities after identities, right? So, I mean, the issue is that which are likely to be useful.
Yeah.
Even in multivariables, we don't know how to go specialize and get such nice things, but maybe somebody else will. So that was the goal of getting there. And this is what attracted our attention. So Liu Kuan Wang has a separate paper with Yi plus Liu plus students. There's a bunch of people, and Liu is still at it. He's still got he's got a new paper recently which he submitted to it's an archive, and he's got another set of one more parameter added, etc.
Okay.
But his techniques are very they are not the Gasper-Riemann type techniques. So that is what was the main motivation for us, was that when Wang and Jin Wang and Zinron Ma did the paper, they got Gasper-Riemann type techniques for one of his results. So then it led to this approach. And I mean, our interest is of course multivariable. So the next thing to do with probably all three of us, Archana, me, and Surbhi, is to generalize this to multivariables. So not the double sums, that won't happen, but these ones will be generalizable easily. So we get elliptic over root systems, and it should be fairly easy to do. I mean, so Michael and I had a paper long back with the multivariable well-poised Bailey lemma matrices.
Okay.
And Halmer had done all kinds of 8v7s. So all the ingredients are there. We have to put it together. That's one.
Yeah.
And so, Steve Milne, we have a special volume in honor of Steve Milne.
Oh, okay.
In Sigma, which Michael is the editor. So we plan to submit that. I mean, Archana, Surbi, and I. That would be nice. I mean, all three students and students type of thing. So that's in progress. So that will be that's multivariable extensions of these last identities, last set of identities. Hopefully, we'll get friendly reviewers because we know the editors.
So Yarma, will you submit a paper to the Sigma? You said that
I thought,
you,
I mean, I
there are
have
many-
these two papers on Roger's Ramanujan. Is that I still didn't submit anywhere.
Okay.
So maybe I submit one of these, because I mean it's not multivariable, but
yes,
I think you mentioned that Roger's Ramanujan is fine.
Yes, that would be fine.
Yeah. Because otherwise I don't have so much like kind of coming up that would be suitable, I think.
Yeah, there's also what you're organizing for Tom Conwinder.
Yeah, there will be
special
a
issue.
special volume for him. Yeah.
Mhm.
So, yeah. So
Nice.
where is that coming? Tom Conwinder special volume?
Yeah, it's in Indagationes,
Okay.
but it's really, I mean, we made this with invitation only.
Okay. Okay.
So some people are invited to submit.
I see.
Mhm.
Yeah. So in fact, a lot of people wrote to us saying that we are already submitting there, and so we don't have anything here. So the invitations were like shortly after your invitations, perhaps.
Yeah.
Yes, but
Of course, I mean, if someone really wants to submit to this Tom volume, then I mean, you could send me an email, but it's mainly for people that have some kind of personal connection to
Yeah,
Tom
yeah.
Conwinder.
Yeah. No, you must have a lot of people like that, right? I mean,
Yeah.
Tom is such a big, he's been around so long.
Absolutely.
Yeah. No, I don't have anything to give, but Atul, you also think of giving something for Steve Milne.
Okay. Yeah, actually, I haven't done the Q thing for a while. I would like to, of course, come back to it.
Yeah.
So I don't know whether I'll be on time, but yeah, I would certainly like to come back to Q series.
Yeah. Yeah, I mean, so Milne had papers in a lot of things related to Ramanujan too. So, for example, he was one of the people who gave a Rogers Ramanujan bijection with Garcia.
Yeah.
And then his 1psi1 was amongst the early extensions of.
Even that long paper in Ramanujan Journal on this R2K of N.
Yeah.
Paper.
So there's some number theory. So yeah, I mean, maybe something you can.
Okay, let's thank